In the vast expanse of the cosmos, where time stretches across eons and space unfurls in endless vistas, there exists a delicate balance between the eternal and the ephemeral. Stars, those radiant titans of the heavens, burn with a steady fury, their light unwavering for billions of years, casting warmth across worlds that orbit in silent reverence. Galaxies, like cosmic clocks, turn with a grandeur that defies the human span, their spiral arms tracing arcs through the void, each rotation a testament to the universe's enduring rhythm. These are the sentinels of stability, monuments to a cosmos that seems at first glance to be built for permanence, a tapestry woven with threads of light that have endured since the dawn of creation. Yet beneath this serene facade lies a truth more restless, more fleeting. For all its majesty, the universe is a crucible of instability, where the very forces that forge stars and galaxies also conspire to tear them asunder. Planets crumble under the weight of cosmic collisions, their surfaces scarred by the violence of meteors. Stars, in their final throes, erupt in supernovae, their brilliance a fleeting cry before they collapse into darkness. Even galaxies, those vast assemblies of light and matter, are not immune, merging in slow, cataclysmic embraces that rend their forms and birth new chaos. The cosmos is a paradox, a realm where eternity and annihilation walk hand in hand, where the enduring is forever shadowed by the fragile. Somewhere, in the uncharted depths of this cosmic sea, there exists an object so precarious, so poised on the precipice of collapse that its very existence challenges the mind's ability to grasp it. This is no ordinary star, no mere planet or nebula. It is a phenomenon born of extremes, where matter is compressed to the edge of reality, where the laws of physics strain under pressures unimaginable. It is a thing balanced on the knife edge of annihilation, a cosmic paradox that hums with the tension of its own imminent demise. Its lifespan is not measured in eons, nor even in years, but in fleeting moments, seconds, perhaps less, before it surrenders to the void. This object, this enigma, is the universe's most unstable creation, a fleeting spark in the dark that burns with the intensity of 1 trillion suns. What is this object, this singular anomaly that defies the cosmos's apparent order? It is dense, beyond comprehension, its substance packed so tightly that space itself warps in its presence. It is violent, its existence a prelude to a cataclysm that could ripple across galaxies. It is fleeting, a momentary flare in the eternal night. Yet, its brevity belies its power. This is not a star nor a black hole in its silent majesty, but something rarer, something more ephemeral, a phenomenon that dances on the boundary between being and nothingness. Its identity remains veiled, a mystery to be unraveled, but its presence, whispers of forces so potent they could reshape the very fabric of reality. What does the existence of such an object reveal about the fate of matter, energy, and the universe itself? Is it a harbinger of chaos? A sign that the cosmos is not as stable as it appears? Or is it a key, a fleeting glimpse into the mechanisms that govern creation and destruction? The universe, for all its grandeur, is a place of relentless transformation, where stability is but an illusion, a momentary pause in an endless cycle of birth and ruin. This object, whatever it may be, stands as a testament to that truth, a reminder that even in the vastness of the cosmos, nothing is truly eternal. To seek its nature is to probe the heart of existence, to ask whether the universe is a clock, winding down, or a canvas forever repainted in fire and light. In the vast cathedral of the cosmos, where stars burn as both beacons and requiems, a faint whisper emerged in 1967, a signal so peculiar it seemed to defy the laws of the known universe. The skies, long regarded as immutable, had begun to speak, in a language of rhythmic pulses, a staccato heartbeat from the heavens. At the Mullard Radio Astronomy Observatory in Cambridge, England, a young astronomer named Jocelyn Bell Burnell stood at the edge of discovery. Her instrument, a sprawling array of wires and antennas, was designed to capture the fleeting flickers of radio waves from the distant reaches of space. Night after night, the telescope listened, its mechanical ears tuned to the murmurs of the universe. And then it heard something extraordinary, a series of regular rapid pulses, arriving with the precision of a cosmic metronome. These were not the chaotic outbursts of known celestial phenomena, but something eerily deliberate, as if the stars themselves were signaling with intent. The signals, dubbed Little Green Men in a half-joking nod to their uncanny regularity, stirred both wonder and unease. Could these be messages from an alien civilization, a beacon from intelligences unknown? The pulses repeated every 1.337 seconds, a rhythm too precise for natural chaos, too alien for human design. Bell Burnell and her supervisor, Anthony Hewish, pored over the data, their charts scribbled with jagged peaks that marked each pulse. The mystery deepened as they ruled out terrestrial interference, radio stations, satellites, even stray signals from passing cars. The source, they determined, lay far beyond Earth in the uncharted depths of the Milky Way. This was no alien transmission, but it was no less astonishing. The discovery of pulsars, rapidly rotating neutron stars that emit beams of radiation, like lighthouses sweeping across the void. To understand pulsars was to peer into the aftermath of cosmic cataclysms. Neutron stars, the dense corpses of massive stars, are forged in the crucible of supernovae, where a star's core collapses under its own gravity, compressing protons and electrons into a sea of neutrons. A single teaspoon of this material would weigh as much as a mountain range, its density so extreme that it defies earthly intuition. These stellar remnants, no larger than a city, spin at dizzying speeds, their magnetic field sculpting beams of radio waves that sweep across space. When these beams cross Earth's line of sight, they manifest as pulses, a celestial Morse code written in the language of collapsed stars. The discovery of pulsars was a revelation, a window into the extreme physics of the universe, where matter is crushed to its limits and time itself seems to bend under the weight of such density. Yet, as astronomers traced the lineage of these pulsating beacons, they stumbled upon an even stranger progeny. By the late 20th century, the cosmos began to reveal objects that defied the already bizarre nature of neutron stars. These were magnetars, neutron stars endowed with magnetic fields so powerful they could rend the fabric of reality itself. Their discovery was not a single moment, but a gradual unveiling, pieced together from cryptic clues scattered across the heavens. In the 1970s, astronomers had begun to notice peculiar bursts of gamma rays, brief and intense, emanating from specific points in the sky. These soft gamma repeaters, as they were called, flickered unpredictably, unlike the steady pulses of their pulsar cousins. Simultaneously, other telescopes detected anomalous X-ray pulsars, objects that glowed with X-rays far brighter than their rotation alone could explain. The connection between these phenomena was elusive, a puzzle whose pieces seemed to belong to different pictures. It was not until the 1990s that the true nature of these enigmatic objects began to crystallize. Astronomers, armed with increasingly sensitive telescopes, observed that these sources shared a common thread. They were neutron stars, but not of the ordinary kind. Their magnetic fields were 1 trillion times stronger than Earth's, capable of twisting atoms into oblivion and generating bursts of energy that could outshine entire galaxies for a fleeting moment. These were magnetars, born from the same supernova furnaces as pulsars, but pushed to an extreme where the laws of physics teetered on the brink of collapse. Their magnetic fields, theorized to arise from the turbulent dynamos within a dying star, churned with such ferocity that they could crack the star's crust, unleashing quakes that rippled through space as gamma-ray bursts. The first confirmed magnetar, identified in 1998, was a revelation that sent ripples through the astronomical community. Known as SGR 180620, it erupted in a colossal flare that briefly outshone every other source in the sky, its energy detectable even from 50,000 light-years away. This event, captured by NASA's Rossi X-ray Timing Explorer, was a clarion call. From a magnetar's heart, a burst so powerful it could have disrupted Earth's ionosphere had it been closer. The flare confirmed what theorists had long suspected. Magnetars were not merely neutron stars, but cosmic anomalies. Their magnetic field so intense they warped the very space around them. These fields, scientists calculated, could reach strengths of 10-15 Gauss, compared to a refrigerator magnet's meager 100 Gauss, capable of stripping electrons from atoms at vast distances and inducing currents in spacecraft orbiting nearby. The discovery of magnetars was a testament to humanity's relentless curiosity, a journey from the rhythmic pulses of pulsars to the violent outbursts of these magnetic behemoths. Each step was guided by the interplay of observation and theory as astronomers wove together data from radio telescopes, X-ray observatories, and gamma-ray detectors. The path was not linear. It was a tapestry of false starts and sudden epiphanies, of signals mistaken for extraterrestrial intelligence, and bursts that defied explanation until the right questions were asked. Magnetars, with their apocalyptic energies and otherworldly physics, challenged the boundaries of what the universe could contain. They were not just objects, but phenomena, embodiments of the extreme where matter, energy, and magnetism danced in a precarious balance. As the 20th century drew to a close, the cosmos had revealed a new layer of its complexity. Magnetars stood as sentinels at the edge of known physics, their existence a reminder that the universe is not a static tableau, but a dynamic, ever-unfolding mystery. They were the offspring of dying stars, yet their influence reached across light years. Their bursts a fleeting signature of processes so alien they seemed to belong to another reality. To study them was to confront the limits of human understanding, to stand at the precipice of the unknown and peer into the abyss. And in that abyss, the universe whispered back, not in words, but in pulses, bursts, and flares, each one a story of creation, destruction, and the relentless churn of cosmic evolution. In the vast, unyielding expanse of the cosmos, where stars burn with quiet fury and galaxies spin in silent grandeur, there exists a class of objects so extreme, so defiant of comprehension, that their discovery sent tremors through the halls of science. These are the magnetars, celestial enigmas born from the ashes of massive stars, their very existence a challenge to the boundaries of physics. Neutron stars, those dense relics of supernovae, were already known as the universe's most compact crucibles, their matter compressed to the density of atomic nuclei, where a single teaspoon weighs as much as a mountain range. Yet magnetars, these rare and volatile offspring, pushed the limits of extremity to a realm where the laws of nature seem to teeter on the edge of collapse. Their magnetic fields, incomprehensibly vast, twist the fabric of reality itself, while their fleeting, cataclysmic outbursts illuminate the cosmos with a ferocity that humbles the stars. To understand the magnetar is to peer into a cosmic paradox, a star that dances on the precipice of annihilation, its brief life a testament to the universe's capacity for both creation and destruction. The discovery of magnetars emerged not from a single eureka moment, but from a slow, disquieting realization. In the late 20th century, astronomers had grown accustomed to the peculiarities of neutron stars, objects so dense that protons and electrons merge into a sea of neutrons, forming a sphere no wider than a city, yet heavier than the sun. These stars, born in the violent throes of a supernova, were already marvels of physics, their surfaces 1,000,000 times denser than lead, their gravity so intense that light itself bends in their presence. Pulsars, a subset of neutron stars, spun with metronomic precision, beaming radio waves like cosmic lighthouses. Yet, in the 1970s and 1980s, astronomers began to notice anomalies, bursts of gamma rays, brief and blinding, erupting from regions where neutron stars were suspected to dwell. These were not the steady pulses of pulsars, but violent, unpredictable flares, some lasting mere milliseconds, others lingering for minutes, their energy output rivaling entire galaxies. The scientific world stood perplexed, grappling with a phenomenon that defied the known behavior of stellar remnants. It was not until the 1990s that the term magnetar entered the lexicon, coined to describe these peculiar objects whose defining trait was a magnetic field of unimaginable strength. A typical neutron star boasts a magnetic field 1,000,000 times stronger than Earth's, but a magnetar's field is 1,000 times greater still, trillions of times more powerful than the gentle magnetism that guides a compass needle. To grasp this scale is to confront the limits of human intuition. If a magnetar were as close to Earth as the Moon, its magnetic field would not merely disrupt electronics or tug at iron filings, it would wrench the very electrons from atoms, distorting the molecular bonds that hold matter together. The atoms themselves would stretch and twist, their once spherical electron clouds warped into elongated spindles, as if reality itself were being reshaped in the magnetar's grip. This is not mere strength, but a force so profound it challenges the stability of the subatomic world, a cosmic alchemy that rewrites the rules of matter. The magnetar's surface is no less a theater of extremes. Its crust, a brittle lattice of ultra-dense matter, exists in a state of perpetual tension, strained by the relentless pull of its own magnetic field. This field, locked within the star's core, churns with restless energy, twisting and coiling like a living thing. At times the crust can bear the strain no longer. It cracks, and in that fleeting fracture the magnetar unleashes its fury. A single flare, lasting less than a second, can release more energy than the sun will emit in 100,000 years. These bursts of gamma rays, the most energetic form of light, streak across the cosmos, detectable by telescopes millions of light years away. In 2004, one such event, emanating from a magnetar in the constellation Sagittarius, bathed Earth's upper atmosphere in radiation, briefly ionizing it as if the planet had been struck by a cosmic lightning bolt. The flare's brilliance was not just a spectacle, but a warning, a reminder that these objects wield power on a scale that dwarfs the stars from which they were born. Yet it is not merely their outbursts that make Magnetar so shocking. It is their fragility, their precarious existence on the edge of oblivion. Unlike main-sequence stars, which burn for billions of years, or even neutron stars, which can pulse for aeons, magnetars are fleeting. Their lifespans are measured in tens of thousands of years, a mere heartbeat in cosmic terms. The source of their instability lies in their magnetic fields, which are not static but dynamic, fueled by the star's internal heat and rotation. These fields decay over time, bleeding energy into the cosmos through flares and bursts. As the magnetar expends its reserves, it slows, its magnetic fury waning until it fades into a quieter, less volatile state. But in their youth, magnetars live on the brink. Their immense density, already teetering at the edge of what physics permits, places them perilously close to the threshold of collapse. A slight increase in mass, a subtle shift in their internal structure, and a magnetar could cross the line, imploding into a black hole, its matter vanishing into a singularity from which no light escapes. This proximity to collapse is what makes magnetars so compelling, so unsettling. They are not merely extreme but unstable, their existence a delicate balance between the forces that hold them together and those that threaten to tear them apart. The scientific shock of their discovery lay not only in their power but in their ephemerality. They are cosmic mayflies, blazing brightly for a moment before fading into the dark. To study them is to confront the impermanence of even the universe's most formidable creations. Each flare, each burst, is a cry from a star that knows its time is short, a signal that resonates across galaxies, carrying with it the story of a universe that is both violent and transient. The magnetar's magnetic field, its most defining feature, is also its most mysterious. Scientists, drawing from observations by NASA's Chandra X-ray Observatory and theoretical models published in journals like the Astrophysical Journal, hypothesize that these fields arise from the rapid rotation and convection within the star's core during its formation. In the chaos of a supernova, the collapsing core spins faster, like a figure skater pulling in their arms, amplifying its magnetic field through a process known as the dynamo effect. Yet the precise mechanisms remain elusive, shrouded in the complexity of quantum physics and general relativity. Some theories suggest that the field is anchored in a soup of superconducting particles deep within the star, where neutrons flow without resistance, generating currents that sustain the magnetism. Others propose that the field is a relic of the star's progenitor, a massive star whose own magnetic quirks were compressed and magnified in death. Whatever its origin, the magnetar's field is a force of nature unlike any other, a reminder that the universe harbors phenomena that push the boundaries of what is possible. The implications of magnetars extend beyond their physical properties, touching on questions that are as philosophical as they are scientific. What does it mean for a star to exist so briefly, to burn so brightly only to fade into obscurity? In their instability, magnetars mirror the broader narrative of the cosmos, AAT, story of creation and destruction, of order giving way to chaos. They challenge astronomers to rethink the life cycles of stars, to reconsider the forces that govern the universe's most extreme objects. Each flare is a data point, a fleeting glimpse into processes that occur nowhere else. Observatories like the Fermi Gamma Ray Space Telescope and the Neil Gehrels Swift Observatory have captured these events. Their instruments attuned to the high-energy cries of magnetars. Yet each observation raises new questions. How do these fields sustain themselves? What triggers their catastrophic outbursts? And what lies beyond the threshold of their collapse? In the quiet of a clear night, when the stars seem fixed and eternal, the magnetar's existence is a humbling counterpoint. It is a star that defies permanence, its magnetic heart pulsing with a restless energy that cannot be contained. Its flares are not merely explosions, but messages, encoded in gamma rays, that speak of a universe in constant flux. To contemplate the magnetar is to stand at the edge of the known, to gaze into a realm where matter, energy, and time are stretched to their limits. It is to witness the universe not as a static tableau, but as a dynamic, ever-changing tapestry woven from threads of unimaginable power and breathtaking fragility. In the magnetar, science finds not only a puzzle but a poem, a fleeting, luminous verse in the grand epic of the cosmos. In the silent expanse of the cosmos, where time stretches thin and the laws of physics bend under unimaginable forces, the universe whispers its secrets through bursts of invisible fire. Magnetars, those enigmatic stellar remnants, pulse with a ferocity that defies comprehension, their magnetic fields threading through the fabric of space like the taut strings of some cosmic lyre. To unravel their mysteries, humanity has turned its gaze skyward, not with eyes, but with machines. Intricate, sentinels orbiting high above the earth, tuned to catch the fleeting screams of these celestial beasts. These instruments, forged from decades of ingenuity, pierce the veil of the visible, capturing energies so potent they ripple across the galaxy and, at times, shake the very atmosphere of our world. High above the planet, the Chandra X-ray Observatory drifts in its lonely orbit, a silent hunter of high-energy light. Its mirrors, polished to near-atomic precision, gather X-rays from the universe's most violent corners, transforming them into data that hum with the raw power of magnetars. Alongside it, the XMM Neutron, its European counterpart, sweeps the heavens with a broader net, capturing the subtle gradations of X-ray emissions. Farther still, the Fermi Gamma Ray Space Telescope scans the sky for the most energetic photons, those gamma rays that erupt from the cataclysmic hearts of magnetars. Together, these observatories form a chorus of mechanical eyes, each attuned to a different octave of the electromagnetic spectrum, each listening for the erratic heartbeat of these stellar relics. In their vigil, these instruments have borne witness to phenomena that defy the orderly rhythms of the cosmos. Magnetars, unlike their steadier neutron star kin, are prone to sudden, violent outbursts. Starquakes, as astronomers call them, where the crust of the star buckles under the strain of its own magnetic fury. These quakes ripple outward, releasing torrents of energy that cascade across light years, arriving at Earth as bursts of X-rays and gamma rays. The observatories catch these fleeting signals, their detectors flaring with the intensity of 1,000 suns compressed into a single moment. Each burst is a clue, a fragment of a story written in the language of physics, hinting at the chaotic inner lives of these stars. No event captured the raw power of a magnetar more vividly than the giant flare of December 27, 2004, from SGR 1806-20. A magnetar nestled some 50,000 light-years away in the constellation Sagittarius. In a fraction of a second, this star unleashed an explosion of gamma rays so intense it rivaled the energy output of the entire Milky Way. The flare was not merely a spectacle of light, it was a cosmic shockwave, a pulse so powerful it briefly ionized Earth's upper atmosphere, disrupting radio communications and leaving a measurable dent in the planet's ionosphere. Satellites across the solar system registered the event, their sensors overwhelmed by a flood of photons that had traveled for millennia to deliver their message. This was no ordinary stellar tantrum, but the most powerful cosmic event recorded within our galaxy in modern times. A reminder of the universe's capacity for both beauty and violence. The data from that flare, meticulously dissected by scientists, revealed a pattern as bewildering as it was illuminating. Magnetars do not erupt with predictability. Their bursts arrive without warning, sometimes in rapid succession, sometimes separated by years of eerie silence. The magnetic fields that drive these outbursts are not static but dynamic, twisting and snapping like overstressed cables. When a magnetar's crust fractures, the energy stored in its magnetic field, billions of times stronger than any field humanity could hope to create, releases in a cascade of radiation. Yet the timing, intensity, and duration of these events vary wildly. Some magnetars flare once and fall silent, others pulse with irregular bursts, as if taunting observers with their capriciousness. No two magnetars behave the same, rendering them among the least predictable objects in astrophysics. The unpredictability of magnetars is not merely a curiosity, but a profound challenge. Each burst, captured by the unblinking eyes of Chandra, XMM Newton and Fermi, tells a story of magnetic fields in collapse, of stellar crusts yielding to forces that dwarf human imagination. These fields, threaded with currents of unimaginable strength, twist and writhe, storing energy like a coiled spring. When they snap, the release is catastrophic, a starquake that sends shock waves through the star's surface and beyond. The observatories record these moments with clinical precision, their data streams painting a picture of chaos ordered only by the laws of physics. Yet, the deeper scientists probe, the more elusive the patterns become. Why do some magnetars flare with such ferocity while others simmer in relative quiet? What triggers the sudden collapse of a magnetic field, and why does it defy the rhythmic predictability of other cosmic phenomena? The giant flare of 2004 offered a rare glimpse into this enigma. The event began with a precursor, a smaller burst that hinted at the turmoil to come. Then, in a tenth of a second, the magnetar unleashed a pulse of gamma rays that carried more energy than the sun emits in 250,000 years. The flare's afterglow lingered for minutes, a slow fade of X-rays that spoke of a star still trembling from its own violence. But it was not just the flare itself that captivated scientists. It was the ripple effect. Earth's ionosphere, that delicate layer of charged particles shielding the planet, quivered under the assault. Satellites detected a surge in ionization, a fleeting disruption that echoed the magnetar's distant cry. This was no mere astronomical event, but a cosmic dialogue, a moment when the universe reached out and touched the Earth. The data from SGR 1806-20 combined with observations of other magnetars, revealed a deeper truth. These stars are not merely objects, but processes, dynamic systems where magnetic fields, stellar crusts, and relativistic plasmas dance in a delicate, volatile balance. The Fermi Gamma-Ray Space Telescope, with its sensitivity to the highest energy photons, has mapped the spectral signatures of these flares, revealing the presence of exotic particles and annihilation events, positrons and electrons colliding in a fleeting burst of light. Chandra and XMM Newton, meanwhile, have traced the softer X-ray emissions that follow, painting a picture of a star's surface cooling after the violence of a quake. Together, these observations suggest a magnetar is not a static entity, but a living furnace, its surface roiling with forces that reshape it with each outburst. Yet for all the data collected, the mystery persists. The irregular timing of magnetar bursts defies simple models. Some flares arrive in clusters, others as solitary cataclysms. The magnetic fields, thought to be the engines of these events, seem to follow no universal script. Theoretical models, grounded in the physics of quantum electrodynamics and general relativity, suggest that the fields are anchored deep within the star, in a superfluid core of neutrons and exotic particles. When these fields shift, they drag the crust with them, triggering quakes that ripple outward. But the precise mechanisms, how the fields twist, why they snap, and when they will do so again, remain elusive. Each magnetar, it seems, is a unique puzzle, its behavior shaped by its history, its composition, and the invisible currents that course through its core. The observatories continue their watch, their data accumulating like pages in an unfinished book. Each burst, each flare, adds a sentence to the narrative, but the story remains incomplete. The magnetars, with their unpredictable fury, challenge humanity's understanding of the universe. They are not merely stars, but paradoxes, embodiments of order and chaos entwined. As the instruments peer deeper, catching the faint echoes of starquakes and the blinding light of flares, they draw humanity closer to the heart of these cosmic enigmas. Yet, with each answer comes a new question, a reminder that the universe in its infinite complexity will always hold secrets just beyond reach. In the vast cathedral of the cosmos, where stars burn as candles against the eternal night, there exists a breed of celestial titans whose very existence defies comprehension. Magnetars, those enigmatic remnants of stellar cataclysms, stand as both sentinels and harbingers, their hearts pulsing with a ferocity that threatens to unravel the fabric of the universe itself. Their magnetic fields, a trillion times stronger than Earth's, churn with an almost sentient unrest, as though the cosmos has imbued them with a restless spirit, a will to both endure and destroy. In this chapter, the narrative of these stellar specters deepens, their instability escalating into a cosmic drama where the stakes are nothing less than the annihilation of matter and the birth of darkness. The question looms, vast and unyielding. Are magnetars the architects of their own demise, and do their violent throes send whispers across the universe in the form of fast radio bursts, those fleeting, enigmatic signals that pierce the interstellar void? The magnetar's core is a crucible of unimaginable forces. Within its dense, crystalline crust, forged at nuclear densities where a single teaspoon of matter weighs as much as a mountain range, Tensions build like the straining of a cosmic fault line. The magnetic fields, those titanic webs of energy, are not static. They writhe, twist, and decay with a rapidity that belies their strength. Data from NASA's Chandra X-ray Observatory and the European Space Agency's XMM Neutron reveal that these fields, stretched beyond endurance, can snap with catastrophic force, releasing bursts of energy equivalent to 1 billion suns igniting in unison. These are not mere eruptions but cataclysms, where the very structure of the star trembles in protest. Starquakes ripple through the magnetar's crust, fracturing its neutron-dense surface with a violence that resonates across light years. Observations of the magnetar SGR 1806-20, which unleashed a gamma-ray flare in 2004, so intense it briefly ionized Earth's upper atmosphere from 50,000 light-years away, bear witness to this destructive power. The crust, strained by magnetic torques, shatters like glass under a hammer, sending shockwaves that ripple through the star's interior, amplifying its instability. Yet this is only the beginning of the magnetar's unraveling. The decay of its magnetic fields is not a slow fade but a cascade, a chain reaction where each fracture begets another. The star's surface, a lattice of exotic matter, buckles under pressures that defy earthly analogy. Neutrons, packed so tightly they blur the line between matter and energy, are torn asunder as the magnetic fields realign. In some cases, the star's core itself may falter. Theoretical models, grounded in simulations from institutions like the Max Planck Institute for Astrophysics, suggest that a magnetar pushed beyond its limits may collapse under its own gravity, its core imploding into a singularity, a black hole born not with a supernova's fanfare, but with a silent, inexorable pull. Such a collapse would be swift, offering little warning, as though the magnetar, exhausted by its own fury, simply surrenders to the void. The possibility haunts astronomers. Could some of the universe's most enigmatic black holes, those without the telltale debris of a supernova, trace their origins to these silent implosions? Amid this escalating chaos, a new mystery emerges, one that binds the magnetar's turmoil to signals detected on Earth. Fast radio bursts, millisecond flashes of radio waves that streak across billions of light years, have puzzled astronomers. Since their discovery in 2007 at the Parkes Observatory, these bursts, fleeting as a heartbeat, carry energies that dwarf the output of entire galaxies. Their origins remain elusive, but a tantalizing clue surfaced in 2020, when the Canadian Hydrogen Intensity Mapping Experiment, CHIME, and the Survey for Transient Astronomical Radio Emission 2, STARE-2, detected a fast radio burst, FRB 2004-28, emanating from the direction of a known magnetar, SGR 1935-2154, within our own Milky Way. This was no distant whisper but a clarion call, a burst of radio energy 1,000 times brighter than any previously observed from a galactic source. Could these bursts, scattered across the cosmos, be the death cries of magnetars tearing themselves apart? The hypothesis is compelling, yet fraught with uncertainty. The energy of a fast radio burst aligns with the catastrophic magnetic realignments of a magnetar's starquake, where twisted field lines snap and release torrents of radiation. Yet not all bursts fit this mold. Some, detected from galaxies billions of light-years distant, suggest other mechanisms, perhaps collisions of neutron stars or exotic processes near black holes. The magnetar hypothesis, while seductive, remains, one thread in a tapestry of possibilities. The instability of magnetars is not merely physical but temporal, as though they exist in a state of perpetual countdown. Their lives are fleeting by cosmic standards, spanning mere thousands of years before their magnetic fields dissipate or their cores collapse. This transience imbues them with a tragic grandeur, as if they are the universe's ticking bombs, their fuses lit at the moment of their birth. Each pulse, each flare, each quake is a tick of the clock, a step closer to oblivion. The magnetar's magnetic field, once a shield against collapse, becomes its executioner, driving stresses that fracture its very being. Observations from the Neutron star interior composition explorer, NESR, reveal that magnetars like 1E 1547.05408 exhibit erratic spin-downs, their rotations slowing as magnetic torques sap their energy. This decay is not linear but punctuated by bursts of activity, as though the star fights against its inevitable end. The question lingers: is each fast radio burst a milestone in this countdown, a signal that another magnetar has edged closer to its final act? The philosophical weight of this instability is profound. Magnetars, in their volatility, mirror the universe's own duality: creation entwined with destruction, order giving way to chaos. They are not mere objects but processes, living on the knife edge of existence. Their magnetic fields, vast as they are ephemeral, destined to fade or erupt in a blaze of glory. Their starquakes, fracturing matter at the edge of physical possibility, remind us that even the most enduring creations of the cosmos are transient. The possibility that they birth fast radio bursts ties them to a larger narrative, one where their private agonies become cosmic broadcasts, signals that traverse the void to whisper of their existence to distant worlds. Are these bursts their final testament or merely a symptom of their ongoing struggle? The answer remains elusive, hidden in the static of the universe's vast symphony. As the magnetar's story unfolds, its instability deepens the mystery of its nature. It is a star that cannot rest, a being that exists to unravel itself. Its magnetic fields, its quakes, its potential collapse into darkness, all point to a cosmos that is not static but dynamic, where even the most powerful entities are subject to the relentless march of time. The fast radio bursts, if indeed their progeny, are not just signals but questions, each one asking, what force drives these titans to their end? The magnetar, in its fury and fragility, stands as a paradox, a beacon of destruction, a herald of creation's impermanence. And so, the universe watches and listens as these ticking bombs count down, their fates intertwined with the mysteries that still elude us, their voices echoing in the silence of the stars. In the vast cathedral of the cosmos, where stars burn as candles against the eternal night, magnetars stand as enigmatic altars, their surfaces trembling with forces that defy comprehension. These stellar remnants, forged in the crucibles of supernova explosions, are not merely relics of cosmic death but pulsating riddles, their very existence a challenge to the laws that govern the universe. Their magnetic fields, a trillion times stronger than those of Earth, twist and tear at the fabric of reality itself, raising questions that pierce the veil between the known and the unknowable. What drives their violent instability? Could these celestial titans harbor secrets that reshape the understanding of matter, energy, and the very scaffolding of existence? As science peers into their hearts, theories emerge, each a thread in a tapestry of speculation, woven from the interplay of hard data and daring imagination. The dance of plasma and magnetism magnetars are not static monuments but dynamic engines, their surfaces roiling with plasmas caught in the grip of magnetic fields so intense they could rend the very atoms asunder. Magnetohydrodynamics, the study of how plasmas behave under extreme magnetic stress, offers a window into their restless nature. These fields, measured in gigateslas, are not mere forces, but architects of chaos, sculpting currents of charged particles into spiraling torrents. NASA's observations of magnetar outbursts, such as those from SGR 1806-20 in 2004, reveal flares so powerful they briefly outshine entire galaxies. These eruptions, scientists propose, arise from the magnetic field's relentless twisting, a process akin to a cosmic spring wound too tight, snapping in violent release. The plasma, trapped in this magnetic vice, writhes and surges, generating shock waves that ripple through the star's crust. Yet the precise mechanics remain elusive. Are these outbursts the result of sudden reconnections in the magnetic field, like lightning arcing across a stormy sky? Or do they signal deeper fractures, where the star's very structure buckles under the strain? The equations of magnetohydrodynamics, intricate as they are, offer only partial answers, their solutions trembling on the edge of chaos, much like the magnetars themselves. Matter crushed beyond recognition beneath the surface, where pressures climb to unimaginable extremes, the very nature of matter transforms. Nuclear physics, which governs the behavior of atoms in the crucibles of stars, reaches its limits in a magnetar's core. Here, atoms are not merely compressed, but obliterated, their protons and neutrons squeezed into realms where the familiar rules of existence falter. Research from institutions like CERN and theoretical models published in journals such as Physical Review D suggest that under such conditions, matter may undergo a metamorphosis. Protons and neutrons, the building blocks of atomic nuclei, could dissolve into a sea of quarks and gluons, a state known as quark matter. This is no mere academic curiosity, but a profound shift where the boundaries between particles blur and the universe experiments with forms of matter unseen since the Big Bang's fiery dawn. In magnetars, where densities rivals that of a mountain, compressed into a sugar cube, this quark matter may form a core, a heart of strangeness pulsing within the star. The implications are staggering. If quark matter exists, magnetars become natural laboratories, testing theories of quantum chromodynamics in conditions no earthly experiment could replicate. The enigma of phase transitions. Yet, the speculation deepens. Could magnetars harbor even stranger forms of matter? Beyond quark matter lies the possibility of strange matter, a hypothetical state where quarks known as strange quarks join the usual up and down quarks in a bizarre alliance. This exotic matter, theorized in papers from the Astrophysical Journal, might form stable configurations, potentially outlasting the magnetar itself. The transition to strange matter would be a cosmic alchemy, a phase shift as profound as water, turning to ice, but with consequences that echo across the universe. If a magnetar's core undergoes such a transition, its structure could destabilize, triggering the violent quakes and flares observed by telescopes like the Neil Gehrels Swift Observatory. These phase transitions, like the cracking of a frozen lake under spring's thaw, could explain the magnetar's instability, each outburst a cry from matter pushed beyond its limits. But the mystery persists. Is this strange matter a fleeting visitor confined to the hearts of dying stars, or could it endure, a relic of cosmic evolution waiting to be unleashed? The cosmic cries of fast radio bursts in recent years. A tantalizing connection has emerged between magnetars and one of the universe's most perplexing phenomena: fast radio bursts, FRBs. These millisecond-long pulses of radio waves detected by observatories like CHIME and Arecibo arrive from distant galaxies, their origins shrouded in mystery. In 2020, a breakthrough came when astronomers traced an FRB to a magnetar within our own Milky Way, SGR 1935 Plough 215 Phi4. The burst, a fleeting scream of electromagnetic energy, carried the power of 1,000 suns. Could FRBs be the death knells of magnetars, their magnetic fields collapsing in catastrophic realignments? The theory suggests that as a magnetar's crust fractures under magnetic stress, it releases shock waves that ripple through the surrounding plasma, generating radio waves that travel billions of light years to reach Earth's telescopes. Yet not all magnetars produce FRBs, and not all FRBs trace back to magnetars. The connection is a thread, not a chain, and scientists speculate that only magnetars in specific states, perhaps those on the brink of collapse, emit these cosmic cries. Each burst is a clue, a fleeting glimpse into the violent heart of a star that refuses to rest quietly. Seeds of cosmic transformation. If strange matter exists within magnetars, its implications stretch far beyond the stars themselves. Some theorists, writing in journals like Nature Astronomy, propose that strange matter could be contagious, capable of converting ordinary matter into its exotic form. Imagine a single strangelet, a tiny fragment of strange matter escaping a magnetar's collapse. If such a particle were to collide with another star or planet, it could, in theory, catalyze a chain reaction, transforming entire celestial bodies into strange matter. This speculative frontier raises a chilling possibility. Could magnetars be the seeds of a cosmic transformation, reshaping galaxies over eons? The idea, while speculative, is grounded in the physics of phase transitions, where stable states propagate like wildfire. Yet the universe offers no easy answers. Observations from the Hubble and James Webb Space Telescopes show no evidence of such transformations. But the timescales involved, billions of years, lie beyond human observation. Magnetars, in this view, are not just stars but potential architects of a new cosmic order, their strange cores whispering of possibilities that challenge the very stability of reality. Cracks in the laws of physics. At the edge of speculation lies a question that borders on the philosophical. Could magnetars reveal cracks in the laws of physics themselves? The concept of vacuum instability, explored in theoretical papers on ArcWeb, suggests that the quantum vacuum, the seemingly empty space that underpins reality, may not be as stable as it appears. In the extreme conditions of a magnetar's core, where energy densities rivals that of the early universe, the vacuum itself could become unstable, triggering decays that alter the fundamental constants of nature. This is not mere fantasy, but a hypothesis rooted in quantum field theory, where the Higgs field's stability is questioned under extreme conditions. If magnetars are indeed windows into vacuum instability, they become more than stars. They become probes of existence itself, testing whether the universe's laws are immutable or fragile. Each flare, each quake, could be a signal of the cosmos probing its own boundaries, a reminder that even the foundations of reality may tremble under the right conditions. A universe that questions itself. Magnetars, with their furious magnetism and unstable hearts, stand as sentinels at the edge of human understanding. They are not merely objects, but questions incarnate, each outburst a challenge to the theories that seek to bind them. From the chaotic dance of plasmas to the dissolution of matter itself, from the cosmic cries of fast radio bursts to the speculative seeds of galactic transformation, magnetars defy easy answers. They are laboratories where the universe experiments with its own rules, where matter, energy, and the vacuum itself are pushed to their limits. As telescopes sweep the skies and theorists wrestle with equations, the Magnetar remains a paradox, a star that burns not with fire, but with mystery. Its secrets, locked in fields and cores beyond imagining, whisper of a cosmos that is not only vast but restless, a universe that questions its own existence as fiercely as humanity does. In the end, magnetars are not just remnants of stars, but harbingers of truths yet to be uncovered, their light a beacon guiding science toward the unknown. In the vast cathedral of the universe, where stars sing their final hymns and the echoes of creation linger in the void, humanity has erected silent sentinels. These are not monuments of stone or steel, but intricate machines, poised on the edge of the Earth's atmosphere or buried deep within its crust, listening to the cryptic whispers of the cosmos. They are the tools of science designed to unravel the enigma of fast radio bursts. FRBs, those fleeting, luminous cries from the depths of space whose origins remain shrouded in mystery. For every pulse detected, a new question arises, and, for every question, a new instrument is forged, reaching further into the unknown. High in the mountains of British Columbia, the Canadian Hydrogen Intensity Mapping Experiment, known as CHIME, stands as a guardian of the radio sky. Its four massive, half-pipe antennas stretching across a landscape of rugged solitude sweep the heavens with unblinking vigilance. CHIME is a poet of the invisible, capturing the faint murmurs of hydrogen gas and, within them, the sharp, millisecond-long bursts of FRBs. Since its first flight in 2017, CHIME has gathered hundreds of these signals, each a snapshot of cosmic violence. Some bursts repeat, like the stuttering rhythm of a distant drum, and a few have been traced to magnetars, neutron stars with magnetic fields so intense they could wrench the iron from a planet's core. These discoveries are not answers, but invitations, beckoning scientists to peer deeper into the hearts of these stellar corpses. Above the Earth, orbiting in the silent vacuum, the Neutron Star Interior Composition Explorer, or NICER, clings to the International Space Station like a barnacle on a cosmic ship. Its X-ray eyes pierce the surfaces of neutron stars, probing their interiors where matter is crushed to densities beyond comprehension. NICER listens to the faint hum of these stars' rotations, mapping their surfaces with a precision that reveals scars left by cataclysmic events. Could these be the crucibles where FRBs are born? The instrument's data paints a portrait of matter stretched to its limits, where the laws of physics teeter on the edge of collapse. Each observation is a thread in the tapestry of understanding, weaving together the story of stars that refuse to die quietly. In the gamma-ray skies, the Fermi and Swift telescopes dance a tireless waltz, their sensors attuned to the high-energy screams of the universe. These bursts of gamma rays, often companions to FRBs, are the death knells of unimaginable forces, collapsing stars, merging black holes, or perhaps something stranger still. Fermi's wide gaze captures the fleeting glow of these events, while Swift, nimble and precise, pivots to pinpoint their origins. Together they form a celestial orchestra, each note a clue to the violent symphonies playing out across billions of light-years. Yet the music is incomplete, the score half-written, as scientists strain to connect these gamma-ray flashes to the radio bursts that haunt their dreams. Beneath the Earth's surface, in chambers carved from ancient rock, the gravitational wave. Observatories, LIGO, Virgo, and Cagra, listen not for light or radio waves, but for ripples in the fabric of space-time itself. These ripples, born from the collisions of black holes or the shuddering collapse of magnetars, are the universe's deep bass notes, felt rather than heard. The possibility that an FRB might coincide with such a ripple tantalizes researchers, for it could confirm a magnetar's death throes as the source of these cosmic flares. Yet, the detectors remain silent on this front, their sensitivity a testament to both human ingenuity and the universe's reticence. Each null result is not a failure, but a sharpening of the question: what force could birth a signal so brief, yet so powerful? The future, however, glimmers with promise. The Square Kilometer Array, or SKA, looms on the horizon like a fleet of ships ready to sail uncharted waters. Spanning vast deserts in Australia and South Africa, its thousands of antennas will weave a net across the sky, capturing FRBs with a precision that could map their origins to individual galaxies. This is no mere telescope, but a monument to human ambition, a tool to chart the invisible currents of the cosmos. When it comes online, SKA will not only detect bursts, but trace their paths through the intergalactic medium, revealing the hidden structure of the universe itself, a cosmic cartography written in radio waves. High above, the planned Athena and Lynx X-ray observatories will join the hunt, their mirrors polished to catch the faintest glimmers from neutron star surfaces. Athena, with its wide field of view, will survey the skies for the X-ray counterparts of FRBs, while Lynx will dive deeper, resolving details so fine they could unveil the magnetic storms raging on a magnetar's crust. These observatories are not merely machines, but time machines, their data carrying echoes from moments when stars were torn asunder, their light traveling for eons to reach human eyes. On Earth, in the humming cores of supercomputers, simulations push the boundaries of physics into realms no laboratory can touch. These digital crucibles model the nuclear collapse of magnetars, where protons and neutrons melt into a soup of quarks and gluons. The equations governing these processes are not mere numbers, but incantations, summoning visions of a universe where matter and energy dance in ways unimaginable. Each simulation is a hypothesis tested, a possibility explored. Could a magnetar's magnetic field, twisted beyond endurance, unleash an FRB in a single catastrophic snap? The answers remain elusive, but the questions grow sharper with every run. These tools, CHIME, NICER, Fermi, SWIFT, LIGO, and their successors, are humanity's outstretched hands, grasping at the edges of the unknown. They are not merely instruments, but extensions of wonder, built to chase a mystery that spans the breadth of the cosmos. Fast radio bursts are not just signals, they are messages, written in a language humanity has yet to fully decipher. Each burst is a fleeting glimpse into the heart of creation, a reminder that the universe is alive with secrets. As these machines listen, watch, and calculate, they carry forward a timeless quest, not to conquer the stars, but to understand them. And in their silent vigilance, they whisper back to the cosmos, "We are here, and we are listening." In the vast, silent expanse of the cosmos, where time stretches thin and the stars hum their ancient songs, there exists a profound paradox. The universe, in all its grandeur, is not a monument to permanence, but a tapestry woven from threads of instability. At its core, this truth finds its fiercest expression in the Magnetar, a neutron star so volatile that its very existence defies comprehension. These celestial embers, born from the ashes of collapsed giants, embody a contradiction. Their instability is not their undoing, but the source of their unimaginable power. In their fleeting, violent outbursts, they cast light across the void, illuminating the delicate balance upon which all existence rests. The mystery of fast radio bursts, FRBs, those enigmatic pulses tied to magnetars, is more than a scientific puzzle. It is a mirror held up to the universe's soul, reflecting a truth as unsettling as it is beautiful. Instability is not the exception, but the engine of creation. Consider the Magnetar, a relic of a star that has already endured its own apocalypse. Its surface is a scarred wasteland, its magnetic field a maelstrom so fierce it could rend the fabric of atoms. Within its core, matter is compressed to densities beyond earthly reckoning, where the laws of physics strain under the weight of their own rules. A single crack in this delicate equilibrium, a shift in its magnetic coils, a shudder in its crust, unleashes an FRB, a burst of radio energy so intense it outshines entire galaxies for a fraction of a second. This is no mere anomaly. It is physics at its limit, reality pushed to the breaking point. The Magnetar does not simply exist, it teeters on the edge of collapse, its instability a testament to the raw, untamed forces that govern the cosmos. To study an FRB is to witness the universe caught in the act of creation and destruction, a fleeting glimpse of a star's final defiance against oblivion. Yet, this instability is not unique to magnetars. It is the pulse that beats through all things. Stars, for all their radiance, are not eternal. They are born, they burn, and they die, their ashes seeding the next generation of worlds. Galaxies, vast and majestic, spiral and collide, their stately dance reshaping the heavens over eons. Even space-time, the invisible scaffolding of the universe, may not be immune to change. Some theories whisper of its expansion, its contraction, or even its eventual unraveling. The cosmos is not a static painting, but a river, ever flowing, ever shifting. The Magnetar, with its cataclysmic outbursts, is merely the most dramatic expression of this truth, that permanence is an illusion, and instability is the crucible, where new realities are forged. This realization stirs a quiet unease. Humanity, too, is a product of this restless universe. The Earth, a fragile speck adrift in the cosmic sea, owes its existence to the violent deaths of ancient stars. The elements in every breath, every heartbeat, were born in the furnaces of long-dead suns, their instability giving rise to life itself. To live is to be part of this grand, turbulent cycle, a cycle that does not promise stability but demands resilience. The Magnetar, in its chaotic brilliance, mirrors this truth. Its magnetic fields twist and snap, releasing torrents of energy that travel billions of years to reach human instruments. In those fleeting signals, there is a message. Existence is not a state of being, but a state of becoming, a constant negotiation with forces that could unmake as easily as they create. What does it mean, then, to inhabit a universe where instability is the foundation of all things? It is a question that lingers like a shadow, both humbling and exhilarating. The Magnetar, with its wild, unpredictable heart, challenges the human longing for certainty. It suggests that the search for answers, whether in the radio bursts detected by CHIME or the X-ray glow captured by NICER, is not a quest for finality, but a dialogue with the unknown. Each FRB is a fragment of a larger story, a story that began with the universe's first light and continues in the silent observatories of Earth. To chase these signals is to embrace the impermanence of all things, to find beauty in the fleeting and the ephemeral. In the quiet of a desert night, where the stars burn cold and clear, the square-kilometer array waits to weave its web of antennas, ready to capture the next burst with unprecedented clarity. In orbit, the future Athena and Lynx observatories will peer into the hearts of neutron stars, seeking the scars of their violent pasts. On Earth, supercomputers hum with simulations, modeling the collapse of matter into realms beyond human reach. These are not mere tools, but extensions of a deeper yearning, a desire to touch the edge of the infinite, to understand the forces that shape the cosmos. Yet, even as these instruments gather data, the universe remains elusive, its secrets guarded by the very instability that gives it life. The Magnetar, with its furious magnetism and its fleeting bursts, is a reminder that the universe is not a place of answers, but of questions. Its instability is not a flaw, but a feature, a spark that ignites the fires of creation. When its magnetic fields buckle and flare, sending pulses across the void, it is not merely a star in collapse, but a beacon, illuminating the fragility of all things. The universe whispers through these signals. Speaking of forces humanity does not yet understand, it tells of a cosmos where collapse is not an end but a beginning, where the breaking of one thing gives rise to another. In the light of a fast radio burst, there is a profound truth. Even in the heart of destruction, there is creation. Even in the shadow of instability, there is light. This is the paradox of existence, written in the language of stars. The Magnetar, the most unstable object in the known universe, is not a failure of physics, but its triumph, a testament to the forces that shape reality itself. As humanity listens to these cosmic whispers, it stands on the threshold of wonder, gazing into a universe that is both fragile and fierce. The signals fade, the bursts vanish, but the questions they leave behind endure. And in that enduring mystery, there is a kind of eternity, not in permanence, but in the ceaseless unfolding of the cosmos, where every end is a spark for something new.